Anyway, 11.1, simple interest. I want to do one more before I move on to the next section. What I want to do is that last one, 15. But say, first of all, simple interest is not how things really work. The idea of simple interest is that you take all the money, you put it into the account, and you let it sit there. And then the interest is calculated all together, all at once at the end. That's what simple interest deals with. And again, that's not how things really work in the real world. That's not how banks operate. But it's a good introduction to how interest works, even though it's not how it really works in the real world. The next section, I'll start here in a minute, is closer to how it works in the real world. Because what they do at banks and so on and so forth, when you borrow money or you put money in a savings account, every once in a while, they look at how much you have in the bank, calculate how much interest you should have, and add it in there. Maybe once a week, maybe once a month. Look at how much you have, figure you should have $5.50 of interest, add it to your account. And they keep doing that month after month or week after week. In the simple interest idea, interest is calculated all at once at the. But even when we get to that section, that's not how it works most of the time either, because most of the time, if you're saving money, you're putting it in a savings account, you don't have $10,000 all at once to put into the account. Under most circumstances, you don't. Usually what happens is you make payments, maybe put in $100 per month into the savings account. And then compound interest is added to that. That's how things normally work. And that's what we're building up to. We're going to look at it from the point of view from a savings account. You're putting money into the savings account, and then reversed. If you are borrowing money and you pay it back with monthly payments, you get a car loan, then you're making monthly payments to pay that loan back with the interest, or you buy a house. A loan to buy the house, they call that a mortgage, and then you're paying it back with payments, monthly payments. You don't pay it back all at once. At the end. But anyway, simple interest is a good introduction to how interest works, though. In this last problem here, 15, the idea is that we're going to compare the exact method, the ordinary method. I mentioned yesterday that to make the math relatively simple, a lot of times they'll just use 360 days in a year, even though that's not really true. It just makes easy math. If we just say a month is 30 days, we have 12 months, so 12 times 30 is 360. Really, there's 365 days in a year, 366 in some years. But in the exact method, we use 365 instead of 360. So the ordinary method is 360, exact method 365. So they're going to want us to compare. 15 says $12,000 is borrowed for 150 days at 7% interest. Calculate the maturity value by the exact method and by the ordinary method. This is the two decimal places. Problem 15. $12,000. $12,000 is borrowed. 150 days. 7% interest. Then if they calculate the maturity value, and do it twice, calculate it twice, once with the exact method and once with the ordinary. Maturity value is what they call the future amount. In our formula, we use an A for amount. So maturity value is referring to the A in the formula. Back up to the beginning here, the loan was for 12,000. That's the principal, the initial amount of the loan. 150 days, that's the T, the amount of time. And 7% interest, that's the interest rate. We need it in decimal form, so 0.07. So there's all the numbers we need to plug into the formula. Of course, the problem is this is in days. We need it in years. So that's why we're going to do it the exact method and the ordinary method. So for the exact method, the time is 150 days. If we change that to years with the exact method, we're going to use 365. So that's how many days there are in most years. So I'm going to plug this in for the T together with the P, R, trying to calculate the plug into this formula here. And you do not need to memorize. $12,000. 1 plus 0.07 for the R times T, 150. 65. So I'm going to do this calculator. Definitely possible to type it into your calculator all at once. That's the right answer. I'm going to do it slowly, though, so that you see what I'm doing. It's very clear how I calculate this. I'm going to do all of this here first. That part, 0.07 times 150 divided by 365. What I've circled there. This long decimal number. 0.0287671. I mentioned it yesterday, but say it again. When you have long decimals like that for intermediate steps, it's best to write them all the way out. Don't round yet, because if you round right now, you could actually get the wrong answer, even though you do everything correctly, just because you rounded, made your final answer be off by enough that it would count wrong. So it's a good idea to write it all the way out. Anyway, next, if I add the 1, One point 0287671 times 12,000. 12,345.20548. So that's the future amount, or what they're calling the maturity value. On to the nearest cent. 0 there right now makes it 5, so I've rounded up to 1. $12,345.21. So for the exact method, maturity value, 1, 2, 3, 4, 5. Two, 1. Now I need to do the calculation again with the ordinary method. What's done under normal, ordinary circumstances. What's done is we use 360. That's 365. That's the only difference. So I'll move that down here. T. Still 150 days. We need it in years. They get divided by 360. Ordinary method, even though that's not really true. It just makes for easy math. Those circumstances, and it just makes easy math to say there's 30 days in a month. Some months have more. Less. We have 12 months, so that's why 360. 12 times 30 is 360. So now if I plug in 12,000 1 plus 0.07. 150 over. This one step at a time again. Do that part there. 0.07 times 150 divided by 360. Plus 0.031 up to 6. And if I add that to the 1, see that? 1.02166667. 12,000. $12,350 exactly. Your calculator may have displayed something slightly different, but when you round, we'd have the same thing. You may have gotten a long decimal place. Might have been 0.0001, like that. Round to 2 decimal places. So the calculation is done. Then they ask some follow-up questions. First one's real obvious. Which method yields the greater maturity value? Which one's bigger? Second. They're close. $1,203. $12,325.21. Second one, $12,350. Slightly bigger for the ordinary method. Ordinary method. Yields the greater maturity value. And then this follow-up question, a little bit more direct, I guess, is who benefits from using the ordinary method rather than the exact method? Borrower or the lender? Keep in mind, the idea is somebody's borrowing money. The borrower is borrowing money. The lender, the bank, is lending it out. And then the borrower has to pay it back with interest. So these maturity values, the amount that has to be paid back. So with the exact method, $12,345.21 has to be paid back. With the ordinary method, a little bit more has to be paid back. So since more has to be paid back with the ordinary method, and that actually benefits the lender, because the lender then is getting more money in return. Or to the exact method. It's not benefiting the lender because they have to pay back more. So it's benefiting the lender, not the borrower. So anyway, that finishes first section, chapter 11 here. Any questions though before I move on? Put it up to questions. If anybody has a question about anything. Move on to 11.2. As I said, this is getting closer to how things really work. Because the idea with compound interest is every once in a while, the bank looks at how much money you have in the savings account, figures out how much interest you should have, and adds it in there. And they do it again later. And of course, what happens is if after month 1, they add in $5 for interest, Then after month two, they're looking at what you initially put in there and the interest they added in previously. You get interest on that. So you're getting interest on the interest they previously added. That's why they call it compound interest. Keeps compounding or adding upon itself. It's still not how it normally works, because the idea is the amount of money is put into the bank in one big lump sum, which sometimes can happen, but most of the time what happens is people make monthly payments. Dollars a month into the savings account. That's not what this section deals with yet. Get to it. Just not. So anyway, in this section, there's a new formula for this new situation. Section 11.2. Compound interest. We've got this new formula that has a lot of symbols that we used previously. It only has one new symbol. A future amount is the principal times 1 plus r over n raised to the n times t power. Now, all of these symbols we've seen in the simple interest, except for the n. It's the only thing that's new. Just to be complete, though, also don't write it all down. Future amount, time, t. T is still the principal. The amount that's initially put into the account, or if it's a loan, the amount initially borrowed. R is still the interest rate. T is still time. The only thing that's new is n. We use n for number of times interest is compounded per year. Number of times. Interest is compounded. So it's the number of times per year that the bank looks at how much money you have in the account and adds in money. How many times they do it a year. First, I want to address this. Just think about figuring out the n, because they don't usually just say the n is 3. They'll say interest is compounded weekly. So we have to figure out the n. I'll make a little table here. Compounding frequency, I'll call it. In the corresponding n. So if they said weekly, 52. There's 52 weeks in the year. Do it once a week. I'll do it 52 times in a year. Monthly, 12 times a year. Daily. Well, here's where we get to that situation again, where sometimes 360, sometimes 360. Now, some of them that can be kind of confusing. Semi-monthly. What would the n be? And in particular, if I compare that to bi-monthly, what would the end be in those situations? Semi-monthly means half a month. So every half of a month, and look at how much money you have in the account and add in the interest that you could have at that point in time. Sometimes they do that on the 15th and the 30th. So twice a month for 24 or for 12 months a year, so 24 times. And it'd be 24. Bi-monthly means something different. Bi means 2, so every 2 months, look at how much money is in the account, add in interest. So if they do it every 2 months, every other month, that'd be 6 times a year. It's easy to get these confused. So that's why I wanted to point those out. They said bi-weekly. Bi means 2, so every 2 weeks. Every 2 weeks. Look at how much money you have in the account, add in the interest. There's 52 weeks in a year, so every other week. This is probably a better way to say it. 6. So anyway, those are the corresponding ends that we use for the different situations. Actually, there's a couple more I want to add. It's right at the beginning, they say semi-annual. Semi means half, annual means year. So every half of a year. If they do it every half of a year, then that'd be 2 times a year. Or if they said quarterly. Quarterly. Quarterly means every quarter of a year. So quarter is a 4, so that'd be 4 times a year. I think that takes care of all the possible situations you might encounter. Look at here to make sure. Takes care of all the situations. So anyway, with that being said, we've got this formula for most of the problems, or what I call plug and chug, just like the previous section where they give us numbers, just gonna plug them in and chug out the calculation. Most of them are relatively straightforward, especially the first few. So just very clear. Say P equals 1,300. A little bit later, as we work through the problems, then they are not as clear. They're still just giving us the numbers, but they're not saying P equals, say, $2,000 is borrowed. Either way, it means you take those numbers and plug them into the formula. So number 1, straightforward problem here. They say calculate the compound amount, use the compound amount formula and a calculator. One day, two decimal places. He is $1,300 borrowed. The interest rate is 7%, and I'll go ahead and change that to decimal form right now. So that's being decimal form. Compounded semi-annually. So that means every half of a year. So that corresponds to 2 times a year. And then the overall time, 10 years. So I've got all the numbers to plug in, calculate the future amount. Plus R over N raised to the N times 2 power. 1,300. 1 plus 0.07 over 2 to the 2 times 10 power. The N is in there 2 times, 2 different places. $1,301 plus I do 0.07 divided by 2, 0.035. And in the same step, I'll go ahead and do the 2 times 10, that's 20. Then if I add the numbers and parentheses there, 1.035. And this is important. Lots of mistakes. This step here, you got to do the exponent next. 1.035 to the 20th. Do that next. .035 raised to the 20th. Big long decimal number. I did not really far, don't round anything yet. 1.989788863. Finally, last step here. By the 1,003. 2,586.72552. Round that to 2 decimal places. 2 right now, next is a 5 though, so I'm rounding up to a 3. 2,586.73. $2,586.73. By the way, I think it's sometimes amazing what happens with these numbers. 1,300 almost doubled, almost 26, almost doubled. It took 10 years, almost 10 years, but that's kind of amazing, and it doubles in 10 years. Of course, unrealistic number here is 7%. Getting 7% interest. Is it really possible? A lot lower than that. But anyway, if you could get 7% interest, you could basically double your money in 10 years. Anyway, another example, number 2. Also just straightforward problem. They give me numbers to plug in. Of course, the numbers are different. We got different compounding. Process is still the same. Two Same formula. NT. Up to, they say the principal this time is $500. The interest rate is 8%, 0.08 decimal form. Compounded quarterly. So quarterly, quarter's a fourth. That'd be 4 times a year. It's 4. And the time, 7 years. So if I plug that all into the formula, future amount, 500 plus the interest rate 0.08 divided by 4. That's 4, and then raised to the 4 and times t. So definitely possible to just type this in all at once. I'm going to do it very slowly. I can go ahead and do that calculation. 0.08 divided by 4. I'll go ahead and do this as well. 4 times 7. I know I have these. Do what's in parentheses first, so I have those. 1.02. Then raise it to the 28th power. (1.02) raised to the 28th power. (1.74024206). Finally, last step times the 500. It's 70.512103. Round to the nearest cent. Right now, next thing's a 2, so I have to leave it. $870.51. And 500 became roughly $870. So kind of close to doubling, not as close as the last problem, but it took a lot less time. Last one was 10 years, this one was 7. And 8% interest. Nearly impossible. Got a whole bunch of these where they just tell you the numbers to plug in. There are a lot of problems in this section. You can see up through 10. They just directly tell you. Actually, the last couple there are a little different. I'll work one of those. I'm going to skip them, but see it's a little different. Like number 8, they're giving you numbers to plug in. But what's different in 8, 9, and 10? They're giving us the future. They want us to calculate what they call the present value. So it's the principal. Idea is if today you took a certain amount of money, put it into an account, and left it there for a while, you want to end up with the future amount, $35,000. Interest is 13%. It's compounded accordingly, and you leave it in there for 10 years. How much do you have to put in there right now? Present value. It's still the same formula. The only difference is it's the P that's unknown. They're giving me a number for the A. Still works the same, just that I want to end up with a little equation to solve. Solve for the P. So number 8. Same formula. Should have erased it. Let's say calculate present value. Just a P. Usually use P for principal, but principal means the initial amount put into the account. So if we put in money right now in the present, referring to the P, they say we want the future amount, $35,000. And they say the interest rate, 14%. Decimal form, 0.13. Compounded quarterly. So it's 4 times a year. And he is 10 years. So plug in everything they give me. A is 35,000. 12,000 equals P is what I don't know. So just leave it P. Parentheses 1 plus R 0.13 over the n, which is 4. Raised to the n times t power 4 times 10. So here's the strategy. I'm going to calculate all this down to a single number. Once I get that down to a single number, I can divide by it. Solve for the P. 5,000 equals P 1 plus this. Point 0.13 divided by 4. 0.0325. And I'll go ahead and do this part too. 4 times 10 is. Next, if I add these. $1.0325. Now I got the stuff down to a single number in the parentheses. And I'm going to raise it to the 40th power. $3.5 42014. I got everything down to a single number on the right side. What I have, think about this as an algebraic equation. I got 3 times that number, so opposite times is divide both sides by that. 3.594. So 3.594201434. 0.1434. One, 2, 0, 1, 4, 4. Just cancel. We're going to divide over here. Nine, 737.90719. Round that to nearest second decimal place. It's a 0. Question is, do I leave it as a 0 or round up to a 1? Makes sense, it's 7, so I round it up. $9,737. $9,700. $7.06. This is another one of those where I think the numbers pretty crazy when you think about them. Because what we just figured out is that right now, if we took $9,737.91 and put it into this particular account, after 10 years, you'd have $35,000. So less than 10,000 up to 35,000. So over tripled, almost quadrupled 10 years. Of course, what's not realistic is 13%. That's really high. But if you could find 13% and you could find nearly $10,000 right now with that account, that will really increase in value after some time. So anyway, 9 and 10 are similar to that. They give you the amount, and they want you to find the present value, the P. 11 is where they start not being so straightforward. They'll say P is 8,000 or is 8%. They're saying it in the form of word problem. Still pretty obvious, I think, but it's not correctly A equals 42,000. Anyway, at 11, time if I do this quickly, it says calculate the compound amount when $8,000 is deposited into the account, earning 8% interest, compounded for 9 years. So 11. Calculate the compound amount. So compound amount, the amount that you have after interest is compounded for something, and find the A. Not in those exact words, but that's what they want to find. When $8,000 is deposited, so that's the principal, the amount initially put into the account. To an account earning 8% interest, so that's the interest rate. 0.08 in this form. And then the money's left in there for 10 years. Why I skipped compounded quarter. That corresponds compounded quarterly. Let's say in this. Anyway, if I take these numbers and plug them in, 8 equals 8,000. 1 plus 0.08 over 4. 4 times I'll do this one just a little bit quicker since I'm about out of time. Do this all at once. Where I was breaking it up. I can do that all at once relatively easily. 1 plus 0.08 divided by 4. Then raised to the 4 times 9, 36. I take 1.02, raise it to 36. 2.039887344 times the 8,000. $1,631.909875. And then there's 10, it's a zero, but the next one's a 9, so I got $1,631.91. Put that in there, it's right, $1,631.91. All right, well, that's all for today. By the way, for some reason I did that too quick or something. Anyway, I'm out of time, so I apologize. I'll continue on tomorrow. See you then. Oh. I just misread it. The decimal point was supposed to be right here. Whenever I hurry, I end up making mistakes like that.